In episode 2, we quantized gravitational acceleration, utilizing the principle of superposition coupled to a Fourier distribution. We established that a large number of transverse electromagnetic plane waves, when added together in a manner obeying a Fourier series, results in an artificial gravitational acceleration field, which may be described quite clearly as space-time engineering. Therefore, if we have quantized gravitational acceleration, we have quantized Newtonian gravity, and by implication, we have also quantized general relativity over the Fourier domain. However, quantizing general relativity over the Fourier domain is not the same thing as relating it to the quantum vacuum. So how do we do it? In this episode, we explicitly relate general relativity to the quantum vacuum. We achieve this by coupling the polarizable vacuum approach to general relativity to Fourier harmonics. The polarizable vacuum approach to general relativity was first developed in 2002. It is an optical model of gravity which is isomorphic to general relativity. Being isomorphic means that it produces the same results as general relativity. Thus, we shall leverage off two primary concepts. That is, experimental relationship functions and the refractive index of space-time. But before we commence relating general relativity to the quantum vacuum, let's do a quick review of a significant decade of unheralded scientific research, which is at the core of the electrogravity-magnetic construct. That is to say, at the core of this presentation. One of the most significant and unheralded periods in scientific history since the development of general relativity and quantum mechanics was the period from 1994 to 2007. Hayes, Rueda, Puthoff, Dobyns and Iveson have done more to advance the physics of the quantum vacuum than most other scientists before or after this period. These physicists asked the fundamental question, what is the origin of inertia? Is inertia an intrinsic physical property, or is it perhaps extrinsic instead? This simple question has largely been avoided by the scientific community. However, the question itself is so profound that it prompted the development of the electrogravity-magnetic construct. References 1 to 8 form the primary considerations, with the polarizable vacuum approach to general relativity being particularly important, as emphasized. We encourage our viewers to review the suggested literature, but for now, we'll move on to the objective of this presentation: relating general relativity to the quantum vacuum. Let's recall a slide from episode 1. This is quite an important derivation. Here you see how all the experimental relationship functions are shown to be equal by the ideal solution for Maxwell's equations involving transverse electromagnetic plane waves. However, what is equally important are the relationships emphasized by the blue circles. This will form an essential relationship shown on the next slide. So please keep this in mind as we move forward. Let's now relate general relativity to the quantum vacuum in 3 simple steps. Step 1. Understanding the wave function precipitation from episode 1. We showed in episode 1 that gravitational acceleration can be related to a cubic frequency distribution utilizing an experimental relationship function. However, Hayes, Rueda and Puthoff concluded in 1994 that the zero-point field, also termed the quantum vacuum, obeys a smooth cubic frequency distribution. Therefore, we may interpret the cubic frequency distribution in this equation as representing the quantum vacuum. Notably, of course, no direct contribution from general relativity appears in this equation. This is the problem we actually need to solve. Step 2. Recalling the emphasized relationships from the previous slide. That is the contents of the blue circles, we may write down gravitational acceleration in the form shown. Step 3. Relating general relativity to the quantum vacuum may be achieved by substituting relationships for the polarizable vacuum approach to general relativity, and an equivalence principle substitution. Once executed, we achieve the required objective by obtaining an expression relating general relativity to the quantum vacuum as indicated. In order to relate general relativity to the quantum vacuum in a complete manner, we need to derive the quantum vacuum energy spectrum. But how can we do it? Well, let's revisit the unit, massive and gravitational harmonic operators we derived in episode 2. We saw that the unit harmonic operator possesses 2 spectra: amplitude and frequency. the amplitude spectrum decreases asymptotically to zero, whilst the frequency spectrum increases linearly to infinity. We also learned that the harmonic modes obeyed an odd-number distribution. That is, all the even-numbered harmonics sum to zero. Hence, only the odd-numbered harmonics were relevant to us. But because we're working in complex form, this means that the imaginary components sum to zero and only the real components remain. In our formulation of harmonic operators, we saw how we can daisy-chain the unit harmonic operator to end up with a gravitational harmonic operator. From the table appearing in episode 2, we can express the fundamental harmonic amplitude as shown. The number 1 denotes the harmonic mode number which has been applied to the calculation. In the case of the fundamental harmonic, the harmonic mode equals unity. The reason that the fundamental harmonic amplitude is particularly important is because it is the only occasion when the amplitude spectrum intersects with the frequency spectrum. As mentioned previously, the amplitude spectrum decreases asymptotically to zero, whilst the frequency spectrum increases linearly to infinity. We'll talk more about this in a moment. Assuming our Buckingham-derived expression represents gravitational acceleration, and may be related to the gravitational harmonic operator by the equivalence principle, it is immediately apparent that a problem exists. This is because the gravitational harmonic operator contains two spectra, amplitude and frequency, whilst the expression for acceleration contains one spectrum, frequency. This difference may be reconciled by synchronizing the frequency spectrum of the acceleration expression with the amplitude spectrum of the gravitational harmonic operator at the first harmonic. That is, when n equals 1. By doing so, it is possible to derive an expression for the common fundamental spectral frequency of both equations. Solving the acceleration equation for frequency, and including a change of notation, yields the fundamental frequency of the quantum vacuum energy spectrum. The fundamental frequency is important because it represents the lowest possible frequency of the quantum vacuum. That is, it denotes the lower spectral limit of the quantum vacuum at any point in a gravitational acceleration field. In other words, the quantum vacuum, or more precisely, the polarizable vacuum, does not exist below the lower spectral limit defined by the fundamental frequency. Immediately, this tells us that the quantum vacuum is not an infinitely broad cubic frequency distribution in the presence of matter. The existence of matter acts to compress the quantum vacuum into a form we term the polarizable vacuum. But we'll talk more about this in the next episode. Now that we have derived the fundamental frequency in the quantum vacuum frequency spectrum, we may effortlessly write down the quantum vacuum frequency spectrum in polarizable vacuum notation as shown. Similarly, we can effortlessly write down the quantum vacuum amplitude spectrum, also in polarizable vacuum notation. Let's now summarize what we have learned so far. An important feature to summarize prior to moving forward is the refractive index. That is, what is it and what does it mean? To best answer these questions, we firstly need to consider general relativity. Appearing on screen is the historically famous solution developed by Albert Einstein, in compact tensor form. General relativity describes how space-time is curved by the presence of matter. We term this curvature as being a manifold. Hence the expression space-time manifold. On the right-hand side of the illustration, you see a two-dimensional representation of how light from a star transits a space-time manifold to arrive at instrumentation on the Earth. Light from the star continuously travels in a straight line, but the path it travels is curved. This is possibly the best example to demonstrate how general relativity works and the value it brings to physics. However, general relativity does have some weaknesses. Firstly, it takes years to master and is profoundly limited. It says nothing about the mechanism for matter to curve spacetime and does not in any way explain why, precisely why, matter curves spacetime. Secondly, general relativity is built to operate across a volume of spacetime in order to map pathways of light. General relativity is a cumbersome tool when considering a single, specific, mathematical point in a spacetime manifold. Hence, a more convenient representation is desired. The polarizable vacuum approach to general relativity solves this problem by the utilization of the refractive index. The refractive index describes what's happening in the space-time manifold, but at a single point. It does this conveniently and succinctly utilizing the value of refractive index. The reason this single-point representation of general relativity is important and valuable is because, mathematically interacting with a quantum vacuum in order to unify general relativity with quantum mechanics, by necessity, requires a single point. Hence, the unification of general relativity with quantum mechanics at a single point can be readily expanded to a space-time manifold. Therefore, the method of single-point analysis reduces complexity and suits the refractive index of the polarizable vacuum approach to general relativity perfectly. Let's now close out this presentation. What have we learned about relating general relativity to the quantum vacuum? We have identified three key outcomes. 1. We have learned that a virtual particle emerges from the quantum vacuum at a single point in space-time, not across a manifold. Therefore, relating general relativity to the quantum vacuum requires single-point analysis. 2. We have learned that the polarizable vacuum approach to general relativity provides a convenient representation of space-time curvature at a specific point in the manifold, utilizing a value of refractive index. 3. We have learned that the presence of matter compresses the quantum vacuum, that is, the zero-point field, from an infinitely broad cubic frequency distribution to a narrow band frequency distribution, bound by upper and lower limits. We will discuss this in a bit more detail momentarily, but for now, let's look at the refractive index. The value of refractive index at a specific position, r, in a space-time manifold curved by mass, m, is given by the equation shown. The solution for refractive index was developed by Depp and Deciato, and denotes a significant improvement over the original Puthoff solution. Most importantly, we derive the quantum vacuum amplitude and frequency spectra, expressed in polarizable vacuum notation. This means that every point in a space-time manifold described by general relativity is simultaneously described by its quantum vacuum signature, as defined by the amplitude and frequency spectra shown. In other words, general relativity has been unified with quantum mechanics. It is worth noting that, for all but the most extreme situations, the influence of the refractive index may be neglected by setting its value to unity. Lastly, we execute a sample calculation for the lower frequency limit of the quantum vacuum at the surface of the Earth, and we find that the quantum vacuum energy spectrum does not exist below the threshold value of approximately 36 mHz. This means that the presence of the Earth has modified the quantum vacuum, that is, it has been polarized, and the lower frequency limit of the quantum vacuum has been forcibly shifted from 0 Hz to approximately 36 mHz. In the next episode, we will derive an expression for the upper frequency limit, termed the harmonic cutoff frequency.